Rotating detonation engines, or RDEs, are an exciting new engine type that utilize pressurized combustion to extract more energy from the propellant. However, the vast majority of research has been done on gaseous fuels, with limited attention on liquids and almost no work on solids. For real-world packaging constraints, condensed phase propellants, meaning solids and liquids, are necessary. As a part of AAE 535, Team SCAR was given the task to design, build, and test an RDE that runs off of solid fuel and gaseous oxygen. Our team began our literature review and brainstormed general system layouts. We found the most logical design was to have three main components: a solid fuel gas generator, or SFGG, that turned the solid fuel into a fuel-rich gas by burning it, the RDE itself, and a manifold that connected the SFGG exhaust to the RDE inlet. We called this component the GGEM, or Gas Generator Exhaust Manifold. There were many challenges that had to be overcome with this design, and there wasn't much literature to go off of since we were in entirely new territory. We essentially had to burn solid rocket propellant, capture the exhaust, and detonate it. Any solids in the exhaust would have to be minimized or captured so they didn't clog up the RDE. It became apparent that our solid fuel formulation was crucial in getting this to work, and the RDE would have to be tailor-made to work with whatever concoction of gases it was being fed. We got to work with NASA's CEA software, and noticed that at low HTPB percentages, carbon in the exhaust was minimized. Additionally, at a certain percentage we saw maximums of hydrogen, carbon monoxide, and methane. None of these are complete products of combustion and could be reacted further. We found a couple fuel formulas that we liked and dubbed the most promising one SCAR Special. Before we could actually start making our parts, we had to set up our test cell, located in Cell C of ZL2. This was an ongoing process throughout the semester, as we needed to set up all our valves, regulators, purge lines, sensors, and data acquisition computers. We also needed to build up our test stand to give our parts a secure location to mount to. Getting our plumbing and instrumentation hooked up was a project in its own right, and slowly but surely, thanks to the hard work and creativity of our team members, things came together. Once our design was complete, we ordered our stock material and got to cutting. To minimize machining time, we did as much as we could ourselves, but the vast majority of the work, including all welding, was done by the talented machinists at Zucro. Before we could test the entire system, some smaller scale tests had to be performed. The first was a simple burn rate characterization of our solid fuel. Knowing the burn rate would help us design a grain that could reach a desired chamber pressure and burn duration. We also decided to have a detonation test that could be run with a small amount of propellant. That way we could test multiple formulations and determine their detonability without having to make an entire fuel grain. This test also gave us a good idea of the detonation cell size, a critical parameter in sizing RDEs. This detonation test was extremely important, as up until then we had no proof of the exhaust detonability. Computer simulations done in CEA and Cantera told us it could be done, but we needed confirmation that it could happen in the real world before we made the RDE. For example, CEA told us that there would be no carbon in the exhaust, but we discovered that this was definitely not the case. However, our ion probe data confirmed that we were absolutely able to detonate the exhaust when mixed with pure oxygen. The final and most exciting test of the semester was the SFGG standalone test. The gas generator was capped with a throat plate sized to give the target chamber pressure. This test was to see how SCAR Special performed in a full-size grain, as well as determine mass flows and characteristic velocity. With the exhaust detonability confirmed and the SFGG functioning well, our team is ready to continue by testing the RDE itself. So far we've been very happy with the performance of our individual components, and we're highly motivated to see this project to its conclusion. The RDE design is complete and is currently being manufactured, with a goal of testing this summer of 2021. Overall, our project achieved our success criteria of having a complete RDE design and multiple tests of a solid fuel that could be burned then detonated. This project would not have been possible without the extensive resources and expertise at Purdue's Zucro Labs, the largest academic propulsion lab in the world. A special thanks is extended to Haynes International for allowing us to use their high-temperature alloys in the RDE. Additionally, we thank Purdue's Bechtel Center and the Zucro machinists for helping us turn our CAD designs into real parts. We're excited to continue working on this project throughout the summer and see how this new engine type performs.